Okay, so today we will be going through on circular motion. Okay. 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 So for today's chapter, right, it is actually an extension of dynamics. Okay, which is your Newton's second law. Okay. So okay, this is actually if you are planning for A-level physics, right, this is actually on the 5th chapter for A-level, just to tell you. Okay. So first thing you all will need to know, okay, is that I think this is the extension from last lesson, which is for an object that is moving at a constant speed in a circular path, is there an acceleration? Why? Okay. So the magnitude doesn't change, even though it's a constant speed, but there is a change in direction. Okay, and velocities are vectors. So because of that, there is a change in velocity and there must be an acceleration. Okay, so that is the main thing that we are going to touch for today, which is what is this acceleration? What is the force? Because F equals ma, right? So what is the force that is needed for an object that moves in a circular motion? Okay. Now, as some introduction on some of the terminology or some of the terms that you need to know. For E, I think this is in E maths, I guess. S equals to R theta. The formula you all know, right? Okay. So this thing called, what is this theta? Okay. For here, we call it angular displacement, which is, if this is at t equals to 0, and you rotate, the angle that it rotates in the time of t is the angular displacement. Okay, the amount, the angle that it rotates, something like this, like displacement like that. But in this case, it's angular, which means that it is going to be measured not in meters, but in radians. Okay, here, I think all learn radians already, right? Anybody haven't learned? Okay, can I? Okay, so next thing is this thing called angular velocity. Okay, this term is known as omega. Omega. O-M-E-G-A. Okay, this is the Greek alphabet. So this is a small letter. The capital letter you all learned before already, which is going to be this. Okay, so when you write this omega, right, it's not W, it's not sharp, it's just curve. Okay, so that is the difference. So it is measured in radians per second. And you can get this formula, V equals to R omega. Okay, so omega is known as the angular velocity, which is the rate of change of angular displacement. Okay, you all have learned differentiation, right? At least the basics. So when S equals to R theta, if I differentiate this with respect to T, R is constant for constant radius, you will get d theta dt. Okay, this, you all haven't learned implicit differentiation. Okay. Another way. You all can see that ds dt equals to ds d theta times d theta dt. You all learned already, right? Okay. So ds d theta is going to be R because R is constant. Okay, so ds dt is actually the velocity, R, and this one is going to be omega. Okay, so from S equals to R theta, you can get V equals to R omega. That's one of the methods. Okay, there's another method, which is that omega being the angular velocity, right? Okay, for something that moves at constant angular velocity, we can have omega equals to 2 pi over t. This is another formula for omega. And why this is so is because to move here one full circle, the time taken is 1 period. And the angular displacement is 2 pi radians. Okay, so it's something like angular displacement over time. So it's like velocity is displacement over time. Okay, a distance equals speed times time, speed equals distance over time, something like that. So in this case, it's the angular velocity. There is the angular displacement. of one full circle, which is 2 pi radians, divided by the time, which is 1 period. So from here, you can also see that the velocity is actually also the circumference divided by time. Circumference is 2 pi r. All right. So you can see a 2 pi over t here. That's how you also can get r omega. Okay. So you can get v equals to r omega in 2 ways. Okay. Last one is on this thing called angular acceleration. We won't be touching it today, but just to introduce to you so that the next lesson we'll be using this. Okay. Next lesson is on rotational mechanics. Just to tell you, that one will be tougher in terms of concepts, but questions probably for Olympiad probably not that tough, I guess. Yeah. So for this, the concepts are easier. They don't really come up as a chapter in circular motion, but they come up in terms of when they link to other stuff. Yeah, later I will show you how it links to electrostatics. You can link to electromagnetism, which I think you all haven't learned yet. And yeah, and to gravitational orbits, which will be the 5th lesson. Okay, all your orbits that you will see in the universe, right? Why the moon orbit around the Earth, why Earth around the sun, why the solar system is flat, all this are all based on this, the concepts here. Okay, so these are like the basics here. Okay. Okay, so next thing. Okay, so anyway, linear acceleration. Okay, just A equals to R alpha, which by alpha is the angular acceleration. Okay, which is the rate of change of angular velocity. Just that we won't be touching this today. Okay, so first thing, okay, just now we established that for an object that moves at a constant speed in a circular path, there is a change in velocity because there's a change in direction. Okay, so because of that, if there's a change in velocity, means that there must be an acceleration, which means by Newton's second law, there must be a resultant force. Okay, now the thing is, there is a resultant force. Okay, there is a force, but we are saying that it moves at a constant speed. So let's say it's speed v here, speed v. At every point, the speed is going to be the same. Okay, notice I use the word speed instead of velocity because the direction is changing. So the speed is constant. What can you say about the work done by the force? It's going to be 0. Okay, so there's a force, but the work done is 0. So what can you say? What can you comment about the force and the displacement when the work done is 0? The work done is 0 because there's no change in K. Okay, the velocity, the speed is constant. But there's a force here. We know that there must be a force because there's an acceleration. No, there's a displacement here. One full circle. So it means that the force, the vector force, is going to be perpendicular to the displacement. Okay, because why? Work done is force times displacement in the direction of the force, or distance moved in the direction of the force. Yes, right. What energy, power. Okay, so because of that, it must be perpendicular. So there's a force, but it doesn't increase its K. It does no work. The purpose of the force will be to change the direction of the velocity. Okay, that's the sole purpose of this force. And this force, okay, being perpendicular means that it can be in this direction or the other direction, correct? So which direction do you think makes more sense? Number 1 or number 2? Number 2, right? Because it's going to turn in this direction, right? So because of that, we can say that this force, okay, the characteristic of this force is that it's going to be perpendicular to the velocity and directed towards the center of the circle. Okay? The name of this force, there's a name for it, it's called the centripetal force. Okay? So that is what this name here means. Centripetal force. Okay, the acceleration will be called centripetal acceleration. So centripetal force and centripetal acceleration, these are the forces. Okay, the centripetal force itself is a force that is required for any object to be moving in a circular motion. Okay? In the 5th lesson, you'll be learning on gravitation. So what will happen is that you'll be learning on forces of gravitation between, let's say, the Earth and the Moon, the Sun and the Earth. Okay? If you look at the solar system, all these objects are moving in circular motion. In this case, around the Sun. Okay? There can be 2 stars that can move around each other also. There's such a thing called binary stars. Okay, so you have like stars that move around each other. So what happens is that the gravitational force between them is providing that centripetal force for the objects here to be moving in a circular motion. Okay, we'll come to that in 2 lessons time, but just know that the base understanding comes from this chapter. Okay. Also, at the same time, it will be good for you all to also look through your O-level stuff if you have time, on electromagnetism. Okay? Yeah, self-learn. Yeah. Have to, Olympiad students, no? Okay? You all will be learning how to, in the chapter, you all will learn this thing called Fleming's left-hand rule, which is an important thing. Fleming's left-hand rule. Left-hand rule, you can practice first. Put a 7, then, everything is going to be 90 degrees to each other, but that one is under electromagnetism. Okay, you can learn that one. You can go and understand that one first. Okay, that will be useful for your Olympiad, because in the Olympiad, what happened is that quite a number of the stuff that are in the competition, right, is going to be from the O-level syllabus. And that will include the entire O-level, including your electromagnetism and electromagnetic induction. Means the last 2 chapters. Okay? So it will be useful for you all to continue on your syllabus beforehand. Means at least look through the textbooks. I believe you all have the textbook. Okay? At least you know the basics is good enough. Okay? If you have time, you can even do the topical TYS. Yeah. Okay, can. So, year up to year, any questions? Okay, all can understand the how the centripetal force and centripetal acceleration come about. Okay, why there is a need for it. Everything is written here, so can reread one more time. Okay. Now, the formula, because now that you know there is a force, okay, so now we come to the formula time. The formula for centripetal acceleration is given by V squared over R. Okay, the geometrical proof is here. But you don't need to know the proof. You can just apply it directly. Okay, the proof is basically if this is the initial velocity and this is the final. If we take Vf minus Vi, that is the change in velocity, which is going to be this. Okay, remember vector subtraction. You'll get on average, because we are taking these 2 points, right? On average, will be at the center. It will be this direction. This will be the change in velocity. Okay. And from here, you can actually see that it is going to be similar to this, where this is R, and S. Okay, just similar only. So the proof from here can show will show you that A equals to V squared over R. It's just more for you to see, but you don't really need to know. Okay, you can just straight away use A, the acceleration being V squared over R, and because V is equals to R omega, and you sub it in, you'll get R omega squared or V omega. Okay, typically you'll be using this one and this one most of the time. Okay, and which one to use depends on the data that's given. So if they give you the speed, you'll be using V squared over R. If they give you the period, usually they give you the period. And you know that period is 2 pi over omega, okay, which is from omega equals 2 pi over t. Okay, because we know this, if they give you the period, it'll be easier to use this. Okay, so it's which one is easier to use, that's about it. Okay, so this is the formula for centripetal acceleration. And from there, because F equals to ma, we have the formula for centripetal force. Okay, so the idea of centripetal force, because it gives you the centripetal acceleration, right? Centripetal force itself is a resultant force, means it's an F net on the object. Just that it doesn't cause an increase in the speed, but it causes a change in the direction. So when we want to calculate centripetal force, we calculate it by looking at the free body diagram and calculating the resultant force. The resultant force itself is the what? Is the centripetal force. Okay, so some examples. Okay, these are some formulas. Okay. So some examples are here where we will first analyze what is a uniform circular motion. Okay, uniform circular motion, being uniform means that the speed is constant. And your centripetal force being mv squared over r. If your speed is constant, usually mass will be constant, okay, because it's the same object. Speed is constant. For the same radius, you have a constant centripetal force. Okay, so it just linked by this formula. So some of the common examples of circular motion are here. Okay, these are more of like the common examples of uniform circular motion. First one is a pendulum bomb. Okay, your pendulum bomb, you all can swing in this, can swing like that. Okay, means like left, right. Okay, or you can just hold it and swing a circle, horizontal circle. Now, when you swing in a horizontal circle, the forces acting on this bob, there are only two, which is the tension and the weight. Okay, so because it's swinging in a horizontal circle, okay, let me just make this bigger. Okay, this is the path. Okay, so let's say it's moving in this circular path, the blue color path. Okay, this is the bob. We know that the centripetal force must be towards the center of this circular path. This is the direction of the resultant force. Now, when you consider the free body diagram on this, there will be one force that is here, which is the tension, and one force which is downwards, which is the weight. So because this is the centripetal force, which again the resultant, your free body diagram will be something like that. When you put in them tip to tail, okay? When you take out the forces, it will look like this, and this will be your resultant. Okay? So you can solve it this way when there are two forces, or when there are more forces, again, you'll need to split them into components. Okay? Up to you, okay? So basically, again, it's an extension of just your dynamics. So in terms of, let's say you want to split the forces up, instead of drawing the tip to tail, you can also resolve the forces in the vertical direction or horizontal direction. Okay, if you resolve in the vertical direction, the vertical here is going to be t cosine theta, whereas here is going to be theta, and horizontal is going to be t sine theta. Okay, so t cosine theta will be equals to mg. T sine theta will be the resultant, and you can equate it to mv squared over r. Okay, there's no acceleration in the vertical direction. So you can see, again, same as dynamics, we are resolving our forces perpendicular and parallel to the direction of acceleration. So perpendicular, oops. Okay, so going to be perpendicular and parallel to the direction of acceleration. Okay, so parallel t sine theta equals to mv squared over r. Vertical t cosine theta equals to mg. Okay, from there, then depends on the question, depends on the data that is given, then you'll be able to solve the questions. Okay, so this is like this is the most simplified case. Now, some other examples that's also slightly simplified here. It is first one here, this one. This is what we call a bank road. Okay, means a road there's a slope. So usually where you see this, right, is roads where there is going to be a circular path. Okay, there's going to be a turn. Or I think in the Olympics, there's something similar for those cyclists to cycle and turn in a circle. And, okay, you'll see that the slope, there's a slope for them. So why this is so is because when you are going at a very high speed, okay, let's say when it's flat, on a flat ground, okay, and you want to go at a high speed. Okay, this one is like front facing. Okay, so the front facing and you're going at a high speed, it's going to turn. You need friction to be able to provide the centripetal force. Okay, so when there's not enough friction, what will happen? The car will slide outwards. It's the same feeling as when you sit in a car and it's going to turn, right? You feel yourself being thrown outwards. Car, bus, anything. You feel yourself being thrown outwards. Okay, but you're not moving because of the friction between you and the seat. That will provide that centripetal force. So far, okay? Yeah. The other example here is motorcyclist, or you can say cyclist, just cycling a bicycle, same thing. When you're going to make a turn, or you see a motorcyclist make a turn, you'll always see them bend. Okay, you cannot turn when you are perfectly straight, not possible. Okay, so we'll see them bend because the reaction force, which comes from the friction and the normal contact force. You want the reaction force, the horizontal component of it, to provide that centripetal force. Okay, but you see, motorcycles can do it, but cars, you cannot turn like it. Okay, so when for cars, right, it's really heavily dependent on friction, right, to provide that centripetal force. So what happens when there's not enough friction is the car will slide and hit something. So that is the reason for this bank road. Okay, in the bank road, right, what happens is that this R is bent. Okay, it's like the normal contact force is already slanted. There is a horizontal component that's able to provide that centripetal force. Instead of totally relying on friction, now the normal contact force is able to also provide that centripetal force. So the advantage is you can actually make a turn safely with less friction needed. Okay, so you can see some of the expressways are actually, some of them, the roads are slightly bent here when you are turning. There's a turn. Okay. The last example here is a normal alloplane. Okay, so you'll see that when an alloplane is going to make a turn, it will actually tilt. Why? Because there's a force that's going to be perpendicular to its wings. Okay, you'll learn this next lesson on Bernoulli's effect. So basically, this lift force, okay, is what we call lift. There is a vertical component. There's also a horizontal component. Again, the vertical component is going to be equal to its weight, but the horizontal component will provide that centripetal force. So it's able to make a turn. Okay, so you can see that centripetal force is always provided by other forces. And when you draw a free body diagram, when you see a free body diagram, you don't have a force that is labeled as centripetal force. Okay, this one is a bit off. Maybe I should have labeled as friction. Okay, so more of labeled as friction than centripetal force. Okay, there's no labeling of a centripetal force on a free body diagram because it's the resultant of all the forces acting on it. Yeah, so if they give you a diagram, ask you which one is the correct one, okay, you will know that this one came out in A level quite frequently. So usually you'll choose the odd one out, but in this case, the odd one out will be the wrong one. If you see such a question, it will be that if they label a centripetal force, right, that will be a wrong labeling of the free body diagram. Okay, it's always due to different forces acting on it. Okay, so up to here, if there's no question, we can start with the first question here. For this case, because for this worksheet, because I have already done the word solution for another school, right? So I think I gave it to you all as well. So you all have the word solution here as well. Okay, so you can also look through. But now we'll just go through the question so that you understand how to apply centripetal force equations. You can look at the first question. Okay. Wait, this is the wrong one. Okay, so for the first question, the airplane is moving at a horizontal plane. Okay, they give you a constant speed. Now it's going to make a rotation. They tell you that the wings are at an angle theta with the vertical. So that's why the vertical is here, the wing is here. Okay, so the angle is here. So because this is theta, okay, here will also be theta. Here is 90 degrees. So within this part is 90 degrees minus theta. Then here is theta again. Okay. Lift force is always perpendicular to the wings. Okay, when you draw it. So now, when the plane in this particular free body diagram, where will be the center of the circle? Towards the left side, right? This is where the center is. So because of that, once you identify where the center is, your centripetal force will be directed towards the center. Okay, so you start by identifying the center of the circle. So your centripetal force will be directed towards it. Okay, so what happened here? Okay, we let the lift force be L. Let this one be weight. We know that L cosine theta, if we take the horizontal component, will be equals to mv squared over r. L sine theta, which the vertical component, must be equals to mg. Equation 1, equation 2. Take equation 2 divided by 1. You'll get tangent theta equals to gr over v squared. Okay, gr over v squared. Okay, let me just use a calculator. 9.81. The r is 60 km. Remember to convert your km to meters. Divide by 780 square, then tangent inverse. You get 44.1 degrees. Yeah. Huh? I mean, different from the previous one here. For here, right? Okay, take note. The angle here is the lift to the vertical. Whereas the question here is the angle, the wing to the vertical. Yeah. Purposely designed to be different. To train you on the angles. Okay, question 1. To the wing to the vertical. the wing angle of theta to the vertical. You know? Okay, question 2. Question 2 is a tough question. The original question didn't have the diagram. Okay, I took it from a university textbook. Yeah. No, but it's the simplest question there. Okay, so it's tougher because there are more things to consider here. Now, I want to use this question to introduce a new term, which is axis. Okay, this thing here, this vertical line here, is what we call the axis of rotation. Okay, because when we talk about 3D objects, okay, it's no longer, it's no longer clear when we talk about a center of a circle. Okay, let's say you have a ball, for example, and we say that it's going to rotate about the center. What does that mean? There are many possible directions, you see. So because of that, we use this thing called axis of rotation. We say it's going to rotate about this axis. Then you know that it's going to rotate. So normally when we analyze circular motion first, okay, instead of 3D objects, right? When we analyze circular motion, right, when we talk about center of a circle, it's more of a 2D plane. So we need to visualize the 2D plane here, and that you know that it's going to be in this is going to be a 2D plane. This will be the center of the circle. Okay, and the centripetal force will therefore be towards the center of the circle. Okay, so that is will be the center of the circle. So when it's going to what this question is talking about is this thing called luggage carousel. Means those luggage, and when you come out of the airport, you're taking a luggage. Okay, now for Changi Airport, this thing is almost flat. There may be a small angle, but we cannot detect. Okay, but there will be some airports that will probably be slightly steeper. Okay, I think I've seen before. So it's like the luggage come out from the top here, then it will slowly let it slide down, something like that. Yeah, then after that, it will slowly come out. Then there will be something to stop it. Okay, but this is just a example question. It's more of a theoretical thing than really applying and really seeing it a lot. Okay. So now what happens is that the luggage is placed on the carousel, not the app, and 7.46 meters from the axis of rotation. So you can see the axis of rotation here. Okay, they gave you that the period is 38 seconds, which means that we are most likely going to use V equals we are going to use A equals to R omega square. Okay, because remember omega is 2 pi over T. Okay, so now you're supposed to calculate the force of friction. Now, for this luggage, okay, I'll give you all the answers straight because this is a more complicated question. For this luggage, let me just zoom in. Zoom in. Okay, big enough. Okay, so we know that there must be a weight downwards. There must be a normal contact force. Now, the key thing is friction. Okay, friction we know is going to be along the surface. Now, is it in this direction or the bottom direction? One or two? Which one will make more sense? Why one? Okay, the key thing here is where is the direction of the centripetal force? It's towards the left, right? For this normal contact force, is there a leftwards component? There isn't any. So it is not able to provide a centripetal force. So we need the friction to be in the direction 1 so that there's a leftwards component to provide that centripetal force. Okay, so this is like the slightly tougher part because of this. to be able to like analyze this part. Okay, so it will be in the upwards direction. Now, you also need to see that because this is 20 degrees here, same in dynamics, this part here is going to be 20 degrees. Yes? Okay, so what happens here? Okay, let me just label the friction first. So this is now the free body diagram. Okay. And if I were to, now I draw a vertical line here. Okay. Remember, when we want to resolve forces, again, we are going to resolve parallel and perpendicular to the direction of the force. So in this case, we will need to resolve horizontal and vertical. Okay, because the centripetal force, which is resultant force, or the direction of acceleration is leftwards, horizontal. So here will also be 20 degrees. At the same time, here is also going to be 20 degrees. Okay, so if I let the normal contact force be N, you'll see that this horizontal component, I call it NX, okay, and the vertical component, I call it NY. NX is going to be N sine 20 and NY is going to be N cosine 20. Okay, and for friction, let's call it, this one I think you can use the red color. Let's call it F. There's also a vertical component and a horizontal component. Okay, so what I'm doing here is splitting all the forces in the horizontal and vertical component because those are the two perpendicular directions that I'm going to analyze with. Okay. Okay, so I'm going to zoom out here. Okay, so to continue, what will happen is that because in the vertical direction, the resultant force is 0, we can say that Fy plus Ny must be equal to the weight. Okay, this is the weight. Or in this case of Fy, F sine 20 plus N cosine 20 equals to mg, and m is 30 kg. So 30 times 9.80. Okay, for yours, 9.80. That's why I use 9.81 here. 9.80. So this is on the vertical direction. On the horizontal direction, we know that Fx minus Nx must give you the centripetal force. Okay, and Fx is F cosine 20 degrees. Nx is N sine 20 degrees equals to M R omega square. Let me just move it up. This will be our equation 1. This will be our equation 2. Okay, so you solve directly using your scientific calculator because you can see that this is going to be a simultaneous equation. 2 equations, 2 unknown. The unknowns are F and N. Okay, make sure your calculator is in degrees mode. simultaneous equation. So it will be sine 20 cosine 20 30 times 9.8. Then the other one is cosine 20 negative sine 20 and 30 times 7.46 times 2 pi divided by 38 squared. Okay. So you'll get your F as 106 newtons and N as 274 newtons. Okay, but only one friction, so it's easy. You still need to solve both anyway. Okay. Okay, good. Okay, good. Next one. Okay, you can read the question. Okay. So the student builds and calibrates an accelerometer, okay, to determine the speed of the car. In other words, the car, okay, in this case, the car is going to turn in a circular path. So there will be an angle. So from there, calculate the centripetal acceleration. Okay. There is a similar question in your TYS, but it's not on circular motion. Okay. In that question, if you look through our TYS, there's a question that is also a car. Yeah, it's on the Newton's second law one. Okay. Then after that, I think they ask you to draw the pendulum when it's moving at constant velocity and when it is accelerating or decelerating. Cannot remember which one. Okay. So in this, so the part when there's acceleration, you know that if it's accelerating forward, it will bend backwards. All right. So that the tension and the weight, the resultant of it will give you a resultant force in the forward direction. So that's why it's accelerating forward. Now, in this situation, it is at a constant speed, but there is still a centripetal acceleration. It will still be something similar, but it will not like be backwards to the car, but to the side of the car. Okay, so it will still be, there will still be a bend. Okay, there will still be a bend. So if you look at the front view, it will look like this. Okay, we let this angle be 15 degrees. Now, the center of the circle will definitely be, in this case, based on this diagram, it will be on the right side. It won't be here, okay? It doesn't turn around here. It turns around a larger radius. Okay. Now, for this case, the tension will be upwards and the weight will be downwards. So for part A, T cosine 15 is equals to the vertical force, which is mg. T sine 15 will be the resultant force, will be equals to the centripetal acceleration. Okay, I will put MA here because the question asks for acceleration. So equation 1, equation 2, Take 2 divided by 1. The tangent will cancel out. Okay, 9.80 times tangent 15. You get 2.63 meters per second square. And for the radius, A equals to V square over R. So R, V square over A. You'll get around 201 meters. Okay, part C, I will leave it for you all to do by yourself. Okay, nothing really special. It's still the same thing, it's just repeating the question where instead of 15 degrees, it's going to be 9 degrees. Okay, but the speed is going to be different. So it will be just the radius that is the same. Okay, the answers is also given to you already, so you can take a look. Up to you, okay? Quite simple, huh? Okay. So now we'll go to the last part of the notes. Which is on non-uniform circular motion. Okay, which means conservation of energy is going to be involved here. Now, for uniform circular motion, speed is going to be constant, but non-uniform is not constant because there'll be definitely changes in energy. Okay, there will be a force that is going to be tangential that causes the change in the velocity. Okay, so we know that again, work done is force times distance moved in the direction of the force. Centripetal forces itself does zero work. Okay, they do zero work. So, and that's because they are perpendicular. So if there's a change in the speed, there must be a tangential component of the acceleration. Okay, so because of that, the net acceleration is no longer towards the center. The centripetal component is, but the net isn't. Okay, there is also a tangential component now, which will either slow it down or speed it up. Okay, so now I will try to explain the tangential component part using this, what we call the loop. Okay, so this is a simplified diagram. Okay, you'll probably see this in those roller coasters where they turn 360 degrees. Something I never dare to see. Okay, so when it moves, okay, as it moves up, right? Let's say as it moves up without any additional energy input, what will happen as it goes up and then come down? Okay, so what will happen is that between this point, the top point, and the bottom, okay, let me just reduce the thickness. Between the top and the bottom, there is a gain in GPE, there will be a loss in KE. Okay, as it goes up, there's a gain in GPE, there's a loss in KE. Okay, because of that, you can see that the speed is going to be going to decrease. Okay, that's why it's a non-uniform circular motion. Okay, so why does it decrease? Let's talk about the forces on what is happening. So let's say as it goes up, what happens here? The weight is downwards. There'll be a component of weight downwards. And there will be a normal contact force that is towards the center of the circle. Okay. For this weight, we can resolve the weight into a direction that is in this direction and this direction. So you can see that this, I call it maybe W Wx and Wy. N minus Wx will be the centripetal force at that point. But there will be a Wy, which is the tangential component. So it causes it to slow down in terms of forces, because the force and the velocity are in opposite direction. Okay, the velocity is this is here, but the force is here. So it will cause it to slow down. Okay, so the same thing happens throughout this entire circle up to maybe, let's say here, as it goes down. As it goes down, there will be again a normal contact force and a weight. This weight again can be split into a component here and a component here. Again, the Wx and Wy. So these two add up, gives you the centripetal force, and this one is a tangential that causes it to speed up. So what happens is that the resultant force is no longer towards the center of the circle. Okay? The centripetal force itself, in terms of magnitude, also changes as it goes along the full circle, because it's dependent on the speed. Okay, it's v square, mv square over r. The radius can be constant, the mass can be constant, but the v is not constant. So when we analyze the question, if you look at it in terms of forces, it is actually harder to analyze, okay, because the forces keep changing direction. So it will be easier to analyze based on conservation of energy. Okay, so that is the first thing to know. Now, second thing is, okay, you can look at the example question. Find the minimum velocity required such that the particle will remain in contact with the track at the top of the loop. In other words, let's say you are giving an initial velocity and you let it go by itself. What is the minimum velocity here so that it will go along the whole track, then comes up? Okay, so here I'm going to show you something. I prepared my water bottle. Okay. Let me do the camera so that those who are not here can see also. Stop share. Hello. Okay. Let me try and rotate. Must warm up. See lah. So what I'm going to do, right? Okay, is to try and turn this water bottle and show you that the water will not come out. I think you have to lower it properly for a warm up. So you can turn around and you see that the water doesn't come out. Okay, turn around for the camera. Let's do one more there. Okay. Okay. You can try it. Okay, the question is, why does the water not come out from the bottom? Okay. Okay, let me turn this back. Okay, let's share back the screen. Okay, so the thing about whether you will come out or not, right, is this thing called in contact, remaining in contact. What does it mean by remain in contact? Okay, to remain in contact, in this case, there must be, let's now make it thicker. To remain in contact, it means that the normal contact force must be greater or equals to 0. Okay, if it's not in contact, then there will be no normal contact force. Make sense, right? So why is that equal to 0 is because when it's equals to 0, this thing means just in contact. Just nice. Okay, when you are able to calculate that it is exactly equals to 0. Okay, if it's like negative, right, it means that it already lost contact earlier. It was equals to 0 in an earlier part of the motion. So if you get n negative for some reason, right? But that means that this one will move along here, go up. If it stops here, then good. Okay, you'll come back now. If it goes a bit more, you'll move in a projectile motion. You cannot let that happen for a roller coaster. Okay. This was CMAX last time, JC Max last time, to calculate this. But it's not in the syllabus now. Okay. So the question now is, what is the minimum speed needed here so that it is able to remain in contact? Okay, that's the question here. So now, before I continue on this, let me explain on the water bottle one. Okay, why the water doesn't drop out. Okay, it's also about this remaining in contact. So for the water bottle, what happened is this. The water is here, right? Let's draw the free body diagram of this water first. The free body diagram will be this weight and the normal contact force. So when we are rotating at the top of the motion, N plus W is equals to mv squared over r. Okay? When we need N to be greater or equals to 0, it means that your mv squared over r minus the weight, which is mg, must be greater or equals to 0, and you rearrange v is greater or equals to square root gr. You need a minimum speed so that it will remain in contact. If it's too slow, which I don't want to try here, the water will come out because it will lose contact before that. So you need a minimum speed of square root of gr so that it will stay in contact with the water bottle and not fall out. Okay, and when v equal to square root gr, it will be just in contact, which means that n equals to 0. Okay? Because if it's anything smaller, it will start accelerating downwards. I mean, it's already accelerating downwards. Your water will start falling downwards, will move downwards. Okay? It will come out, it will spill. This same reasoning is the reason why at the International Space Station, the astronauts are floating. So at the International Space Station, right, the gravitational field is not 0. Okay? They are still weight. Okay? If you look at your TYS, there will be one of the years, the MCQ, right, is that they also talk about the International Space Station, and they mentioned that at that location, the gravitational field is 5 meters per second square. Okay, so the reason why the astronauts are floating, okay, let's say this is Earth, and then your ISS is around. Okay, this one is a little bit linked to 2 chapters later. Is that there is a gravitational field, there's the gravitational force towards the center of Earth on the International Space Station. Okay, and this is also the same as the field strength is the same for the astronauts as well. Okay, so at a particular location, at a particular speed that is moving, okay, this one is you can do by calculations later for when you learn a chapter of gravitation. They will be moving in such a way that the n is equals to 0. That's why they are floating around. Okay, they are not in contact with the surface of the space station. Okay, the other in this case, right, what we call, right, when n equals to 0 for them, right, is what we call, there's a term for it. It's called apparent weightlessness. Okay, so why the word apparent is because they are not weightless. There's still weight, but the normal contact force is 0. The acceleration of the astronauts and the International Space Station are the same there. Okay, both are at free fall. Okay, but this one not really linked. I say a bit off. N is equal to 0, but this one is, yeah, actually, yeah, correct. It's just that the weight, in this case, the weight provides the entire centripetal force. Okay? But there are more to it there. Okay? This is just a simplified explanation for it. Okay, let's go back to the question here. So again, the question is, find the minimum speed such that you'll remain in contact. So the only way to analyze, right, is to start analyzing from the top part. And from the top part here, we know that N is, okay, for the remain in contact, N greater or equals to 0. Or to simplify your calculations without inequalities, we want it to be just in contact, it'll be equals to 0. So because of that, mv squared over r equals to mg, or mg equals mv squared over r, and we get this. Okay, same as just now. So that is the speed required at the top of the motion, so that it will still be in contact. Any slower, it will lose contact. Any faster, it will still be in contact anyway. So that's the minimum speed. Okay? So now that you get the minimum speed, we want to find the speed at the bottom. Between the top part and the bottom part, okay? I'll put here, maybe I can add in from bottom to top, from the bottom to the top part, there will be a gain in GP and a loss in K. So the gain in GP, mg2r, because the height is 2 times the radius. And loss in K, loss is always the initial minus the final. Okay, there's an initial K, there's a final K. Because we are considering by the magnitude. So initial will be larger than final, so that's why there's a loss. Okay, so when you rearrange the answer, you'll get this as the minimum speed needed at the bottom, so that at the top it still remain in contact. Okay, even if I mean that is if you don't have any additional input of energy. Okay, so the main new thing here is just about remaining in contact. Okay, now there's an extension of this. We can also take a rope. Okay, just imagine you take a rope and you turn around. The rope or string, when it's straight, right, we call it taut. So what is the speed, or what is the minimum speed needed so that the string is, there's also a term called just taut. Okay, so same thing, when it's taut means that there's tension. Just taut means that tension is just nice 0. Okay. Well, okay, now you can try question 4. Okay, same thing when you approach the question, your free body diagram, okay, and determine where's the center of the circle and hence the direction of the centripetal force. Okay, the free body diagram of the car is just a normal contact force and the weight. Okay, no need to bother about each wheel. Okay, that's too complicated. So you take a simple one, just the normal contact force. And because the acceleration or the resultant force is going to be downwards, okay, because the center of this rope hump is below, so the center will be downwards. This is the direction of the centripetal force. So your weight minus N equals the centripetal force, okay, which is mv squared over r. So mg minus N equals to mv squared over r. You get your N equals to mg minus mv squared over r. Okay, M is given 1800, v squared r. Okay, so let's see, v squared over r. 8 squared divided by 20 minus 9.8 times 1800. You get 11880 newtons. Okay, it's always about drawing the free body diagram. What is the maximum speed as it passes the highest point? What it can have, okay, without losing contact. Regardless maximum minimum speed, you can always set N equals to 0 to solve. You could also set or solve by inequality if you want to. Okay. So to simplify things, you can just use N equals to 0 to solve. But here I'm going to use inequalities to show you. Okay. So for N greater or equals to 0, we know that if you make N the subject, which is going to be this. Okay, this is going to be here. So mg minus mv squared over r greater or equals to 0. Okay, rearrange v less than or equals to square root gr. (9.8 times 20). And after that, square root, you'll get v less than or equals to 14. So the max speed is 14. Okay. Okay, next question. Question 5. So this is where the string question comes in. Just thought. Okay, so you can see it's pretty similar. First thing, again, free body diagram. Okay, then equate the forces to the centripetal force. Okay, after you determine the direction of the centripetal force, then you equate them. Then after that, just solve it. If find a speed v for which the particle should be projected for it to be just hot at C. Same thing, we are going to do conservation of energy. Okay, so from B to C, there's a loss in KE equals gain in GPE. Loss again is going to be the initial speed minus the final speed. In this case, V square minus GL equals mg to L. Okay. Take note, this one is the initial. This one is the final. Okay, so this one is the VF. The M cancels out. Square root of 5GL. Okay, question 6. Okay, I think should be quite standard here. Okay, part 1 is just V squared over R. Part 2, at the highest point, there's N and mg. So N plus mg equals to MA. Okay, remove the C. The N is not zero all the time. It's special case when you say just in contact. So for this case, N is not zero, you're supposed to find it. Okay, so N equals to the mass times acceleration minus mg. So minus 9.8 times the mass is 60 kg. Yeah, so you get around 646. Okay, this one was using 9.81. So for Olympiad, you'll be using 9.80. Okay, so there will be some slight differences on the last answer. Okay. Now for part B, okay, this one, B part 1 should be simple. This one is within your Sec 3 work. Okay, just change in GPE. You'll get around, in this case, 8232. Okay, again, 8240 is because 9.81 was used. So using 9.80 will be 8230. Okay, so we'll use the Olympiad version of the gravitational acceleration. Now, so from top to bottom, you can choose from bottom to top or top to bottom. It really doesn't matter. Okay. In this case, there will be a loss in GPE, which is equal to the gain in KE. Okay. Loss in GPE 8232. Gain will be the final KE minus the initial KE. Did they give it was 12. Okay. So half 60 V square minus 12 square. Okay, because the final is larger than the initial. So 8232 divided by 30 plus 144 square root. I get 20.455, okay, which is around 20.5. Per second. Okay. Okay, so now you can try some of the Olympiad MCQs. There are only a few in the past. Okay, but that's because circular motion is like the foundation to the next chapter, and also to other possible chapters. Okay, like example, okay, before I go through the MCQ, example, you can have, let's say for you learn the model of an atom, right? So you have, let's say your nucleus is a positive nucleus and you have an electron that's orbiting around it. So why is the electron orbiting in a circular motion around the nucleus? Okay, this one is regular, unlike charges attract. So the attractive electric force is the one that is providing that centripetal force. But this is a simplified model of an atom, of course. Okay, so this is how you can explain it. You can even calculate it, just that you don't have the formula for this for now. Okay. You also have, you all haven't learned electromagnetism. Yeah. That one is for you all to learn. So what happens is that for electron moving in a magnetic field, let's say magnetic field, we can also call it B field. Okay. There will be a force that's going to be perpendicular to it. And you also move in a circular path inside. This one came out in the 2017 Olympiad. Okay. Yeah. So it will be in those questions that they can come up. And also another chapter called gravitation. Okay. Which will be touched in two lessons times. Okay. Okay, so you can look at the first few questions. Okay, so far only came out a few only. Okay, let's just go through all. There's enough time to go through all. Only 9 questions. Okay, first question. the first thing you will probably see is what is 4 revolutions per second? Huh? You can see as frequency. You can also see you can also use it to calculate the angular velocity. Okay, so there are a few ways to do it. Okay, so first way, yeah, you can say frequency f is equals to 4. So t is equals to 1/4 and omega 2 pi over t. Actually, 2 pi over t you can also put as 2 pi f. Okay, so from here you can get 8 pi. Another way is to see that 4 revolutions, 4 complete circles is 8 pi radians. 1 revolution is 2 pi. So from here you can also see that omega is 8 pi immediately. Okay, so what is the magnitude of its acceleration? Or r omega square. Because in this case, omega is given. Okay, so this one is just r omega square. Pretty straightforward. Okay, remember to convert to meters. Times 8 pi square. You will get 13. Answer C. Okay, understand this already. Now you can try question 2. Pi turns per minute. Okay, so for question 2, 5 turns every minute means the omega is 10 pi over 60, 8 radians per second. This is a uniform circular motion, so we don't really need to consider much. Okay, so you just take r omega square, pretty straightforward. Okay, now I can try question 3. you all should be able to get these two formulas. Okay, the problem is, what is the radius? Yes. Okay, good. So from here, equation 1, equation 2, 2 divided by 1, tangent 22 equals to V squared over GR, where R is 2.1 sine 22. Okay. So I get V as 1.76. Is that the answer? Yeah. Okay. Which is around 1.8. Okay, answer C. Okay, so this one answer C. Okay. Okay, for question 4, it's pretty straightforward. M3V squared over R just erase this part. Okay. This is the new centripetal force minus the original is equal to 64. Okay, so we get 8 mv squared over R equals to 64, or mv squared over R equals to 8 newtons. Okay, so answer is just 8 newtons. Okay, question 5, I'll just give you the answer straight. Okay, you can just read it. Okay, because this one sometimes goes a little bit counter to what you see when you hold a candle. Okay, the thing is, when you hold a candle and you walk, you'll see that it bends backwards because of air resistance. But when you have this gas jar, right, it blocks all the air. There's no air resistance. So what will happen, right, is that this flame will actually bend towards the center. Okay, it will actually be like that. You can actually find videos of this on YouTube. Okay, you can just search for candle in jar in circular motion, something like that. Okay, so you can search on Google, then after that, the videos will come up. Okay, so because of that, you'll just point inwards towards O. So answer is just D. Then this type of question in the Olympiad, right, will be the fastest to do. So you might want to look at all the questions first sometimes, okay? Because some of the questions may take longer. Especially mechanics, usually the questions will take longer to do. Okay, so far when I do the past paper, it's like that. So it's like the front part that actually takes longer, but the behind part actually is faster. Okay. Okay, question 6. You see, this is the extension of the last week one. Okay, when you have two objects with an acceleration, just that it's in a circular motion here, but it's the same thing. Okay, so the acceleration, when you draw your free body diagram, okay, you speed them up, and the acceleration is going to be r omega squared. Okay, remember centripetal force is the resultant force. So for A, T minus T1 is mr omega squared. For B, T1 is m times 3r over omega squared. Okay, because the radius is 3 times, but they have the same angular velocity. Okay, so because it's 3 mr omega squared, you can see you can have this relation. T1 is equal to 3 times of this one. And then you just make T1 the subject. Okay, already can go question 7. Okay, question 7 is pretty straightforward. Actually, one equation is sufficient. Okay, just nice because you are using omega, so use mr omega squared. Okay, the radius will be L sine theta. Okay, 2016, the questions were a bit interesting. Okay, they are like they were like related to each other quite a fair bit. So that's why you have a question 8 here. L is 0.8. Wait, L, there's no omega square here. Okay. Okay, question 9. Okay, this question 8. Why I start with this, because you can see that for question 7, this part was not used. So that's why I start with it. Okay, question 9. 360 kg roller coaster series. Okay, you can see does not leave the track, means in contact. Okay. We use n equals to 0 to calculate the limit, so it's easier. So it can be the maximum or the minimum, it doesn't matter. We just know that that's the limit. Okay, the maximum or minimum value. Okay, that will work with that based on logic. Okay, so for n equals to 0, this is just in contact. At here, mg equals to mv squared over r. Okay, by right, it's supposed to mg plus n. So n equals to 0. So v squared equals to gr. So that is the speed that is just in contact here. Okay, so it's at rest here. Now what happens is that between these 2 points, let's say start point to end point, there's a loss in GPE, which is equals to the gain in KE. Okay, here V equals to 0, so it's pretty straightforward. Loss in GP, mg 120 minus 2r. Okay, gain in KE, half mv squared. Because initial K is 0. So we cancel the m. G times 120 minus 2r. I'll bring the half over. V squared is gr, okay, because we have it here. So now I cancel the g also. 240 minus 4r equals to r. 5r equals to 240. So you divide by 5, you should get 48. Any questions so far? Yeah, so up to here. So for today, mainly just like that, okay, for circular motion. The only thing that that's new is the idea of centripetal force. Okay, and then the formulas of centripetal force being mv squared over r or mr omega squared. Okay, and for you also, you learn what is angular velocity. That's about it. Okay, okay. Let me just stop the thing.